Hi, it's Graham Cox here, co-founder of OptiSurface, and I'm going to give you a quick rundown on our latest case study from our website called Azerbaijan Bay Irrigation. It basically is a cotton irrigation field that's being converted to bay irrigation. It's part of a larger farm of 600 hectares, 1,500 acres in Azerbaijan. And it is farmed already, but it needs to be graded or landformed. And we're going to focus on this one field here in the farm. You can see that it's currently split into a couple of three different fields with a smaller halved sections here. Well, we're going to combine that into one field with a number of bays across it. So this indicates, or this is the existing topography, quite low slope, well, good slopes actually for bay irrigation. But if you do our drainage analysis on this with furrows, you'll end up with, this is where water will pond. You can imagine after each irrigation, if there's water lying in these areas, that's not 800, that should be 80 actually. 0.08. So it's actually up to, these purple areas are over 80 millimeters deep of ponding within the furrow. And you could see that would cause a whole heap of problems with waterlogging a crop, and uniformity of irrigation, poor uniformity of irrigation, excess irrigation water required because all these things have to fill up. All these depressions have to fill up before it'll run through the furrow to the end of the field. And these get, waterlogged, oversaturated. So yeah, this is why you do landforming for surface irrigation, because you do not want these depressions holding water. Any depression that holds water will cause waterlogging and problems with machinery access. You can't get in and plant, spray, harvest when you want, because these areas remain wet and your machinery can get bogged in them. So you've got to wait till these areas dry out before you can do any machinery operations, and by then these other areas could be too dry. So it's just it shows you the importance of improving your terrain, your topographies, to promote uniform drainage and infiltration. Okay, so the solution, so there's the existing topography again. The solution was to design bays with a minimum slope of 0.1% and a maximum slope of 0.2% and zero cross slope in the bays, along with a smoothing factor of 100 meters per percent, which means it smooths the slopes, between these two, the min and max slopes. It can only happen over a longer distance. It won't allow it to jump instantly. That's what the smoothing does. That's the result. Now, to get the bays to work like this, we've got exclusion zones here running perfectly in line with the calculation grid. So you define the main slope direction. That's what this black arrow is indicating. So it's straight down the field, and then when you calculate the first time, you'll see points where it calculates on say a 10-meter grid across this whole field. You can use that to place these exclusion zones so they're perfectly running down the row of grid points. And then what that allows it to do is step across, so you can, the elevation from this bay to this one, there's a step in this case. Those contour lines are about 40 millimeters. So you can see there's a step there of about 80 millimeters, two contour lines, right? So there's 80 millimeter step between that one. Here it's even more. Looks like it's about 160 millimeters would be the step. So that allows the OptiSurface optimization calculation to come up with the best elevation for each of these. It is balancing across the whole field. However, you can get it to balance within each bay if you want, but this is currently balancing completely across the field. So you can see there's zero cross slope because these contour lines are going perpendicular across the bay. So there's zero cross slope and there's just slope down the bay. If we look at the cut fill map, you can see there's a bit of cutting on the uphill side and filling on the downhill side in the cross slope direction to get that zero grade across the field. And also you can see that there'll be deeper fields in some areas which will be filling these depressions in as well, so make sure they drain through. Okay, so that's the design. Results were 237 cubic meters of soil per hectare, which is about it's about 120 cubic yards per acre. Most of the cuts and fills are less than 100 millimeters. Now, one final step is that they wanted to put in a headland, a head ditch at the top of the field to siphon irrigate out of it. So so basically the requirement was to design a head ditch with a pad, which is this line here, to give a minimum and maximum height requirement into the field. So if we look at this long section across the headland, which is the top of the field, this purple line here that steps, that's actually the field elevation, the designed field elevation after the earthworks is finished, the landforming is finished. And then we need a head ditch with water in it, with water higher than the field, to drop. So the siphons go over this dirt embankment here and drop into the furrow here. So this is the furrow height. This is the water height, and basically we needed a minimum and a maximum height that we could drop in. And so basically we're trying to create a head ditch that has the least number of steps in it and a minimum fall height. So you can see, so this is where the pad is built to. So that's this elevation here. So you build the pad to that height, and then you use a grader to grade these head ditches out, the embankments out, to give you this finished embankment here. And then you fill the embankment up with water. You have a check at each of these points to hold the water back, and then the water will be at this height. That's the design height. And then you can see there's a minimum height to fall from that water level down to the furrow height, which will be this HW. And then so it's the furrow will be below this field height once you furrow it up. So there's a minimum height there, and then there's a maximum height here. To get uniform inflow to these different bays, they would need to use different siphon sizes. So you can see there's a lot more head driving the water into this bay than there would be driving into this bay. So this one would need a large diameter siphon. And we did do the calculations on this, but it was something like a 50 millimeter inside diameter siphon for this one, and this one here you could come back to something far smaller. Maybe it was 25 millimeter or something to get the same inflow because there's a lot more head driving the flow through the siphon. And there are tables to define these heads and flow rates for different diameter siphons. So once this was constructed, they were going to trial different siphon diameters in each of these bays to work out which diameter siphon is required to get the water to the end of the field in the target time. So if you don't have enough flow rate, then it'll take just too long to get to the end of the field. Infiltration will be too slow. So what you're trying to do is get the water to this end of this field in a target time, and then you cut the water off the top there and the water will keep flowing down here. But the target time depends on the soil type. So say this soil type has an optimum target time of, let's say, 16 hours. Then you need larger, and if you test it with a siphon that's say only 40mm diameter and it's not getting down in time, the first irrigation is a lot slower because it can be wetting up at full profile. But let's say the second irrigation, if it's taking more than, say, 16 hours to get down for this soil, then you would trial a larger diameter siphon. Okay, thanks for watching. If you have any questions, please contact us. Visit our website at OptiSurface.com or email us at support@OptiSurface.com or give us a call. Thank you.